Okay, so let's take a look at question 1 of the quiz. So you know the mass. So the mass is given, and these guys are hanging it with 3 vertical chains. So what does the word vertical mean? Straight up and down, right? So it's just all to the y-axis, just like that. Because they are all the same rope and they are all the same angle, basically 90 degrees, right, from the object itself. Each of them are going to be the same tension. Makes sense? Because it doesn't say that each the ropes are different. You'll assume that they are the same rope and they're all vertical. That's what it says here. So what you're going to do is when you write the equation, you got Ft1, Ft2, and Ft3, and that is equal to Fg. Okay? So that's balanced forces right here, the net force being 0. So what you could do is, if you know the Fg, m times g, because you know the mass, you just divide that by 3. That's pretty easy. And I think everyone got that one correct. So no question there. Okay, enough said. Number 2. With number 2, you have the angles, the 3 ropes, the 3 chains are now 25 degrees from the vertical. And I was marking some papers, and your angle has to be taken from the vertical. And this is the vertical. The vertical is the y-axis. So you have to measure it from there. Which means you could do this 2 ways. If you do it this way and say, here's the rope, right? You could measure it so that this is 25 degrees from the vertical, which makes this also 25 degrees from the vertical. Okay? That's called transversal rule, also known as the Z rule. See the Z? It's not even the Z, but you know what I mean. So this angle is the same as that angle. They're congruent. Okay, so the mistake that I saw here is that labeling the wrong angle. Okay, you got to make sure that you have the right angle there. So from the vertical, you have to measure it from the y-axis. Okay, because the ropes are all the same again, and they're all the same angle. So if you have the same theta for each one, they will have the same tension force. Does that make sense? Okay, and you just take that, because that is the tension force from the first question, 245 newtons. Okay, so then you'll just consider the angle here. So 245 divided by cosine of 25. And you get 270 newtons. Let's talk about concepts here for a second. You have 245 newtons, it is, if it's vertical. But when you have this thing here, which is 25 degrees from the vertical, this is the rope now compared to this. Why is this more tension? That means the chances of breaking this rope would be greater if you angle it as opposed to just hanging that mass. Why is that? Why does that make sense? Okay, well, look at the force here. This is pulling the mass up. Basically what it's doing. See these lights? The cable is pulling that light up to prevent the Fg from pulling it down. Does that make sense? It's a state of static equilibrium. When you angle the rope, 2 things are happening now. The light is being pulled up, but it's also being pulled sideways. Does that make sense? So if you pull something at an angle, now you're doing 2 things. You're pulling it up and you're pulling it sideways. Now you're looking at the Ft being the hypotenuse of those 2 forces. And that's why angle is going to be, the greater the angle, the more pushing you're going to get in the X and Y direction, and your tension is going to be more. So your chances of breaking the rope is greater. So you're better off just leaving it vertical. Okay? Number 3, I didn't have enough room here, so I put it on a piece of paper. Sorry, I didn't give you enough space. I'll give you more space on the test there. So here is number 3. Okay, so this is the situation. So when I drew it, this is 35 degrees for the tension on the left, and on the right it says is 59 degrees. So I call the first one Ft1, the second one is Ft2. Now remember, the Ft is the actual rope. There's the actual rope, that's Ft1. This is the second one. That's the FT2. And then you just break it down into there's FTY and there's FTX. Okay? 1 and 1. So I'm just going to call this X and this is the Y. Alright? You need to start by drawing the free body diagram because your equation depends on this free body diagram. Once you have that, we need to split it up into X and Y component. And I put the X here. I usually put the X first, but for some reason I put the X here. Okay, so here's what's happening in the X. Net force on the X is 0. Okay, net force on the X is 0. So FT1X is equal to FT2X. This, I know most of you, I think 100% of you know how to do that. That means there's no side-to-side motion. In the Y component, you got the up forces, FT1Y and FT2Y, is equal to the downwards force of FG. Okay, so that's crucial. Once you get to that, you're halfway there. The next thing that you're going to do is you're going to expand what you have. So what's the FT1Y? Well, it's this side right here. It's the vertical force, right? So again, your frame of reference is the angle that you have labeled here. So you're going to go opposite over hypotenuse. You're always going to use the hypotenuse because that's the actual rope. These ones are just imaginary forces. It's not really there. Okay? FT1 is the actual rope. So you're going to have to use that. That's what you're looking for anyway in some question. In this question it is. So opposite over hypotenuse, that would be so. That's sine. That's why I put there FT1 sine 35. And the second one is FT2 sine of 59. And that's equal to FG. So now what I do is I look at the two equations that I have, the X and the Y, and I pick the simpler one. So I'm going to pick the simpler one, which is the X, and I isolate one of them. You could isolate either FT1 or FT2. It does not matter. It's just by substitution that we do this. So I pick FT1. So FT1 is FT2 cos of 59, which is angle 2, divided by cos of 35, which is angle 1. Okay? So that's my FT1 equation right here. Right there, first of all. And so I took that and I put it into the y-axis, which is here. You see this? That is this. That's it, by substitution. Okay? And put everything here so that I only have one variable to solve for, FT2. And you're just putting the like terms. Now from here on, it's just pure math. Okay? The most important thing here is know how to write the FBD equation from the picture and know how to expand it. And the rest is substitution. So there's your FT2, solve for FT2. Your FT2 is 64.4. So now I put this back into the equation right here to solve for FT1. So FT1, here's your FT, this is FT2, which is a 64.4. I put that over here, and you still have cos of 59 over cos of 35, and the whole thing adds up to be FT1 of 40.4. As you can see here, FT2 is greater than FT1, so rope number 2 will break first. It is going to be stretched first because this is 59-degree angle as opposed to 35-degree angle. Make sense? The greater the angle, the more pushing you're gonna get. Okay? Only when at 45-degree angle, and that's when it's equal. Okay? X and Y will be equal. So the greater the angle here, the more pulling in the X direction you'll get. The answer here is rope number, what's that? The one with the 59-degree, or rope number 2 will break first. The rope on the right. Okay? So that's number 3. Number 4 is almost exactly the same thing. So you're finding the tension force on each side of the cable. So this guy here, again, the angles are different. Yeah, so different angles, different angle, you'll have different tension. That makes sense, right? So you actually can't say that the FG is divided by 2. It's not, because the FT1Y and FT2Y are not the same because of the different angle. So you do the same thing. So you do that. You write the FBD equation. Here's what's happening on the X. Y is, can you guys tell me, why is the net force on the X 0? How do you know when to make it 0? How? It's not moving side to side at all. Net force is 0. There are two situations where the force is 0. When there's no motion, or when it's moving at constant velocity. Okay, so you can have static and dynamic equilibrium. Just gonna jump here for a second. When you get to lesson 3, which is the incline here, the net force may not be 0. You know why? Because sometimes it's actually sliding down and it's accelerating. So it's not always 0, okay? You can't assume that the net forces are always 0. It's not. It can have an acceleration. But this one is. On the y-axis, okay, the force up right there, and the other force up, okay, in this case, the FTY, that one, and this one is equal to something. So you're looking at the vertical going up is equal to FG going down. Okay? So that's our equation. Once you have the equation, this is where you expand it. You're taking things apart, and then you can put it back after you've fixed it. Okay? So if you're not sure how to go from here, because I know you all are good at free body diagrams. I see that. And I know that you can go from a picture to the equation. I see that. This is where sometimes it starts to get confusing. So all you're doing is you already have FT1 of X. What is FT1 of X? This one right here. So what is FT1 of X? Well, I have to have a hypotenuse because that's FT1. So I'm looking at adjacent over hypotenuse. So that's cosine. Okay, you answered your own question. Okay, good. So, and the same thing here for FT2, because they're equal, you just will know that's equal to FT2. So FT2x right here. So adjacent again from 48, because 48 is where you're looking at from. So this is your adjacent H. So your adjacent and your hypotenuse, that's cos. So cosine of 48. That's just trigonometry from here to here. Okay? Once you have that, expand, isolate, unite. Those are the steps. The last step, unification. Okay? So you write the FBD. You start with the FBD. Step 1, FBD. That comes with the equation, FBD equation. Then expand on the equation, isolate it, and then unite them. All right, so here we go. Once you have decided what you're going to isolate, there you go, FT1 isolated, you put it into there, right there, because FT1 is FT1. And you combine them. Okay, so here's what we found out. Without looking though, without actually looking at the numbers, you have 35 degrees and 48 degrees. Which one do you think is going to be a greater tension force? 35 or 48 degrees? 48 degrees. Remember what we just said? The greater the angle, that means you're actually being, you're now indicating the tension force on both sides, X and Y. And we calculated that, and as you can see, FT1, the one with the 35, is 476, and FT2 with 48 degrees is 582. So again, FT2 is greater than FT1 because of the angle being greater. And again, which one will break first? So you could actually kind of know this when you're looking at chords, like angles. The more angle it is, the more likely that it will be the first one to break. Okay? So now you know. So I want you guys, when you go out there and you're looking at things that are being supported by cables or anything that is held by something, these are the best way to hang something. It's just vertical, right? The moment you, why would you angle something anyway? Why would you angle it? Why not just hang everything vertically?
Sometimes you can't. More support.
Yeah, sometimes that's the best support, right? It depends on the structure. Maybe you need to extend it out of the wall, right? And there's no way that you can hang it directly above. So you'll need to be creative. So that's when the architects come in and make things look pretty.
So the larger the angle,
The more tension force you'll have.
So if it's 90 degrees, this vertical, why is it?
Oh, okay. So when you're looking at, this is the rope now, right? You actually have no angle. In terms of relative to that, you actually have no angle. So it's, again, you go, does that mean it's 90 degrees? You actually have to start from here. So this is 0 because you're looking at the string. That's your frame of reference. We are not using the Cartesian coordinate in this case. So you're looking at this, that would be 0 degrees. And then when you go like that, that would be the theta. So whatever that is, in this case, 35, whatever angle you're given. So your frame of reference is actually the hanging, the vertical one. Yeah. And so that's 0. There's no angle at all. The tension is minimum. Yeah. Last one. So Phoebe on spring break dragging her suitcase because her wheels broke. Okay, so dragging, the word dragging, what does that tell you? If she's dragging something, what kind of force should be present here? Frictional force. She's dragging something, right? That's why wheels are invented, right? Wheels are invented by cave people to actually make that dragging force minimum. So dragging and sliding, those are clue that you should have frictional force here. So when you're asked to sketch the free body diagram and label all the forces involved, you need to have force there as well. Okay? And it should be there unless it says frictionless or negligible or ignore friction. Okay, so there's your FBD. Determine the normal force. Okay, again, I didn't write my X force right here. What are the forces on the X? Net force on the X is FAX minus FF. And the net force on the Y? Net force on the Y is FAY plus Fn minus Fg. Why would I say that's 0, by the way? Why is that 0? There's no up and down motion. That one you know for sure. How about the X? Is that also 0? How do I know? What's the word in that sentence that tells you it is actually 0? Constant speed. Constant speed, constant velocity, 0 net force. Okay? So there you go. So to find that normal force, you need to get it from here. So FAY plus Fn equals Fg. Oh, it's already right here. And then isolate the Fn and you have 132. Now, let's just quickly go over some sig figs. How many sig figs should I actually have here in my final answer? And I know Nick corrected, he put the number of sig figs there and I go, oh yeah, he's right. I should actually have this as 2 sig figs, so that should be 130, okay? This one should be 90 Newton. And again, how do I calculate the frictional force? So you know that frictional force is mu F of n, but that is not the only way to find frictional force. You can find frictional force from that equation, mu F of n, or from the FBD equation. In this case, we'll have to go with the FBD, okay, which is Fa of x. Okay, so that's just Fa cosine theta, 95 newtons. The coefficient of friction right here. Don't make the silly mistake of doing the math wrong, okay? You know that frictional force is mu F of n. When you isolate the mu, just check your math, okay? Not naming anyone, but you know, if you reverse that, your frictional force will be over 1. Okay? So, careful with your... you have two kinds of coefficient. There is the static mu, the mu s. You can have the static coefficient of an object at rest and you're trying to move it. That means you gotta overcome that. And there's the mu k, which an object that's already moving and experiencing that friction, right? So a mu of s can actually be less than or equal to, it can go maximum of 5. And this would be less than or equal to 1. Why is the mu kinetic less than the mu static? Why is it? And we actually looked at that because remember when I was pulling that block, every time the more I pull it, the applied force that I need to apply, which is the frictional force, actually became less and less over time. When objects are in contact and then they start to move them, heat is generated. And sometimes molecules, when when motion happens, friction, okay, heat is generated and the molecules start to move faster. And something happens at the molecular level and that I don't want to get into right now. Okay? All right. Any questions about the quiz?